This segment we're going to be talking about a simple Brayton cycle, which is used to model a gas turbine power plant. So we're going to limit the discussion to power cycles here. So we're not going to talk about gas turbines that are used in propulsion, so used in aviation, for example. We're just talking about power cycles here. These are also known as combustion turbine plants or CT plants. They can be used by themselves, so alone. And when they're used like that, they're used to kick on during times of peak load. They can operate over extended periods if you need them to, but they are typically more expensive to run because they have relatively lower thermal efficiency. So you typically don't want to run them over extended periods of time if you don't have to. They can also be used in a combined cycle plant. North Carolina has several of these. And what this is, we might talk about these in more detail when we talk about vapor power cycles. But all I want you to know right now is that these are two types of cycles that are just kind of put together. So what you have on the top, you've got a gas turbine engine. And we'll talk about this in this segment in more detail. Remember, with a power cycle, you've got heat coming in, some of it's converted to power, and then some of it is rejected as waste heat. Well, in this case, the stuff that would be rejected as waste heat in that gas turbine plant is just fed into your vapor power plant at the bottom here. So that becomes the QN for this vapor power cycle. So it's just a little bit more efficient. We're going to limit the discussion now to the gas power cycles that are operating alone as a freestanding unit. Okay, so here's what that looks like, and we're looking at this little section in the middle. So you've got air coming in to a compressor, it's being compressed, then it's being fed into a combustion chamber, and fuel also comes into that combustion chamber. You've got a combustion reaction, and what comes out are the products of combustion. Those high temperature, high pressure gases expand over those turbine blades, cause the turbine blades to spin, and then they leave as exhaust. So your compressor requires work, your turbine generates some work to you. So that's what's really going on. Our model is going to be really simplified. Number one, we're going to make air standard assumptions like we typically do with these gas power cycles. So my working fluid is air. I'm not worrying about the fuel. All I'm worried about is air, or in my model, I'm just treating it like it's air. And the other thing I'm going to do is I'm going to replace that combustion process, which I'm not really ready to analyze right now. I'm going to replace that combustion process with a heat addition process, so simple heat addition process. And then I'm going to replace the exhaust process with a heat rejection process. So if you look at the picture up at the top there, you don't see a heat exchanger up at the top. You don't see one at the bottom either. You see a combustion chamber, but you don't see anything up at the top. So just imagine this sort of an imaginary heat exchanger. You're just using it to model the exhaust process. So just keep that in mind. All right. So what we're going to do is we're going to walk around this cycle, and we're going to look at what equations we can use for each of those four processes. So the first process from state 1 to 2 is an ideally isentropic process. So you've got air coming in at 1, it's leaving at 2, and then of course that compressor requires some kind of work or power input on your part. If I make air standard assumptions and I draw my boundary like this, if I want to apply my first law and I'm like, okay, well, is it an open or closed system? Well, I know this whole cycle operates on just one closed loop, or at least that's how I'm modeling it. But this particular device, the way I've drawn my boundary, I have mass coming in, I've got mass going out. So this particular system is an open system. So I need to apply the open system form of the first law. And I'm also going to make sure that I put it in subscript form. So this is what the first law looks like in subscript form. This is the equation that I'm going to be starting with for each of these four processes. All right, well, I'm going to go ahead and assume that this thing is operating at steady state, and that's usually a good assumption to make. The only time you couldn't make that assumption is if you're bringing it online or you're bringing it offline. It's isentropic, so that means it's adiabatic and reversible. So adiabatic means I can get rid of those Q's, and the compressor requires work. I'm not getting work out of it, so I'm going to get rid of that. And I'm going to go ahead and ignore kinetic and potential energy changes. So all I'm left with is this guy right here. And then if I apply my conservation of mass and I know that this thing is operating at steady state, what that tells me is the mass flow rates at the inlet and the outlet are the same. And so my W dot N equation gets even simpler than it was before. So there's my first law. Because I've got air and I'm assuming it behaves like an ideal gas, I can use the ideal gas law, no problem. I'm also going to define the pressure ratio. So this is R with a little subscript P. This is just the ratio of pressures after and before compression. And then I can bring that definition into my isentropic relationship for an ideal gas, which I can use because I have an isentropic process for an ideal gas. And this ratio right here is just equal to the pressure ratio. All right, so that's my first process. My second process from 2 to 3, this is where I'm modeling that combustion process, and I'm modeling it as a constant pressure heat addition process. If I make air standard assumptions and I apply my first law, and I make the same assumptions that it's steady state, I'm ignoring kinetic and potential energy changes, I don't really have any work that I need to worry about, and I have a Q in, not a Q out, what I'm going to be left with is this guy right here. And let's see what else I can do. Well, I'm working with air and I'm assuming it's an ideal gas, so I can go ahead and use my ideal gas law. And I can simplify this even a little bit more because I know that P2 and P3 are equal to one another. And then, of course, my specific gas constant, I've got the same thing on either side of the equal sign. So I can get rid of both of those and just simplify it a little bit more if I needed to. All right, so now let's go to the third process from state 3 to state 4. So it's expanding within a turbine. I get some amount of work out, and ideally that is happening isentropically. So if I apply my first law, this is what I'm left with. Everything cancels out except the W dot out. It's isentropic, so no Q dots or anything like that. And then I can use my ideal gas law, no problem there. And I can use an isentropic relationship because I have an isentropic process. You'll notice I didn't use that from state 2 to 3 because that was definitely not an isentropic process. All right, now let's look at our last process from state 4 to state 1. And this is where I'm modeling that exhaust process. So I'm modeling it as a constant pressure heat rejection process. So P1 and P4 are equal to one another. And if I apply my first law, there's no work, there's no kinetic or potential energy changes. I'm assuming that everything's operating at steady state. This is what I'm left with. And I can apply my first law, or not my first law, but my ideal gas law. And then I can also see that, well, since P1 and P4 are equal to one another, I can kind of simplify that ideal gas law just a little bit and get rid of those pressures and the specific gas constants. Those go ahead and divide out. So let's see, I'm almost done. But there's one additional thing I can do. I noticed that since there's not a pressure drop from state 4 to state 1 or 2 to 3, and that comes because the reason that we can say that is because this is an ideal cycle. Everything's operating reversibly, meaning we don't have any fluid friction, which would cause a pressure drop as the air flowed through that heat exchanger. So P1, P4, P2, P3, those are equal to one another. I can go over to that isentropic expansion from 3 to 4, and I can put that isentropic relationship, instead of in terms of P4 and P3, I can put it in terms of P1 and P2. And then I know that this is just the inverse of the pressure ratio. So there we go. Almost done. Let's see about that thermal efficiency. How do we define that? So this is equal to thermal efficiency. It's defined as big W over big Q. Big W net out over big Q in. So either in the numerator and denominator are going to be either in kilojoules or BTU. All right, so I can also divide through by delta T, get this in terms of power and heat transfer rate. And I could divide through by my mass flow rate, which should be the same throughout the whole cycle if this thing is operating at steady state. And that'll get me things in terms of little w and little q, or something that's in terms, on the top and the bottom of kilojoules per kilogram or BTU per pound mass. And I can go back and look at what I just did with my first law applied to each of those individual devices and get things in terms of enthalpies. I can also put it in terms of 1 minus Q out over Q in, and sort of the same thing. Going back to my first law applied to each of those heat exchangers there. All right, one more thing we want to talk about, and that's the back work ratio. So some of the power generated by that turbine is used to power the compressor. So as the turbine blades spin, it also helps to spin those compressor blades. And the proportion of that work is expressed as a back work ratio. So this is the work of the compressor over the work of the turbine. And typically for a gas turbine engine, it's pretty high. about 40 to 60% of the power that's generated by that turbine is used to run the compressor. And that's just because it takes a lot of energy to compress a gas. So, all right. Well, I know this was a lot of information. We'll work quite a few problems with this the next time that we meet. Thank you for watching.